Hello, everyone. Welcome to the Math Magician's Den. We're going to talk about continuity again. And in this video, first of all, we're going to talk about the existence of a limit one more time, because limits are the basis for continuity. When you guys look at this notation right here that I'm underlining, do you notice the negative next to the C? That's a limit from the left. This is the left-hand limit. When you have x approach C and there's a little plus afterwards, that's the right-hand limit. And the left-hand limit and the right-hand limit have to be the same. Now, the reason I discuss this is because this next definition for continuity on a closed interval, we haven't talked about that yet. If you've watched my previous videos on continuity, we talked about continuity at a point. We talked about continuity on an open interval, but we have not talked about continuity on a closed interval. So let's draw a graph that's defined on a closed interval from f of a to f of b, and let's just draw a curve in there. And what has to happen if you want a function to be continuous on a closed interval? The limit as x approaches a from the right has to be f of a. In other words, we say f of x is continuous from the right at a. Watch my red pen here. As I move in from the right and I approach a, it had better approach f of a, or it's not going to be continuous at that endpoint. I'm going to do the same thing from the other end. The limit as x approaches b from the negative side, from the left, has to equal f of b. This is said to have a function be continuous from the left at b. Watch the green curve. As I approach b from the left, it had better approach f of b. If that doesn't happen, you do not have continuity at an endpoint. For example, on the right hand or on the left hand side of here, if I'm approaching a from the right and it doesn't approach f of a, you can see that's going to end up being a problem, because f of a comma f of a is the endpoint. If it goes up here, you've created a discontinuity at an endpoint. All right. Now, I want to make sure I just erase that. There are certain rules and properties for continuity that we're going to talk about as well. And you're going to notice that these rules for continuity sound a lot like our rules for limits. If you take a constant times a function, you can take a constant times the limit. It's the same thing for continuity. If you take a constant times a continuous function, and sine of x is continuous from negative infinity to infinity, it's continuous on the entire number line. Well, 5 times sine of x would also be continuous everywhere. If you take two functions and you add them together, you could add their limits. If you subtracted them, you could subtract your limits. Well, here we're adding two continuous functions. Both are continuous everywhere, so the result would be continuous everywhere. Same thing with multiplication. You multiply functions, you can multiply their limits. Well, if you multiply continuous functions that are continuous everywhere, they are going to create a function that is also continuous everywhere. Now, division is always a problem. Division, when we divide, I have to make sure the bottom does not equal 0. Well, sine of x is continuous everywhere. X squared is continuous everywhere, but x squared can equal 0 at x equals 0. So we cannot include 0 if I want to describe where this function is continuous. It is continuous everywhere except 0, because there's a discontinuity there. In this case, there would be a hole, because sine of 0 is 0. X squared at 0 would be 0. 0 over 0 creates a hole. Now, these functions are continuous at every point on their domains. We've already talked about polynomials being continuous everywhere. Polynomials are continuous on the entire number line. Radical functions. If you look at square roots, cube roots, their domains are either 0 to infinity or all real numbers, and they are continuous on that entire domain. Now, this is where people run into problems. Rational functions have discontinuities. They have asymptotes. They have holes. But rational functions, everywhere except the holes, everywhere except the asymptotes, they are continuous on those intervals. Same thing with trig functions. Trig functions have asymptotes. In between those asymptotes, each of those pieces is continuous. An absolute value v, an absolute value function looks like a v. It's continuous everywhere. You could draw the whole thing without picking up your pen. Exponential functions are continuous everywhere. They're continuous on the entire number line. And logarithmic functions, if you take a basic logarithmic function, they are continuous from 0 to infinity, but guess what? That's their domain. Can you think of a function that is not continuous on its domain? I am thinking of the greatest integer function. The greatest integer function looks like this. In some schools, in some books, some teachers will teach it this way. Sometimes it will have double bar brackets on it. But what happens is it starts at 0, goes to 1, but then jumps. It always goes close to open, close to open, close to open. It jumps at every integer. And here's the thing. The domain of this is all reals, but it has a discontinuity at every integer. This function is not continuous on its domain. Now, the other thing is, if you have a composite function, just make sure your inside function is continuous at C, and then make sure your outside function is continuous at the inside function at C. So if I want to do f of g of x, g has to be continuous at C, and then f has to be continuous at g of c for the entire composite function to be continuous at C. Now, we're going to talk about how to find some discontinuities on these last several problems. And I'm going to start with the easiest one that I can think of, and that's a rational function. And what I want you guys to always remember with the rational function, you should not just factor the bottom. We all know the discontinuities come from the bottom. But if I factor the top, I'm going to get x plus 5, x minus 1, and on the bottom, I'm going to get x plus 7 and x minus 1. Now, what I want you to notice here, I want you to notice that there is a factor that cancels from the top and the bottom. Now, wait a minute. The original function, that x minus 1 was in there. So I have to set x minus 1 equal to 0, and I'm going to get x equals 1. That is a discontinuity. But since it was removed from the equation, it is a removable discontinuity. In fact, this gives me a hole. Okay? It's a removable discontinuity because it was removed from the equation. Now, there is another factor right here. It was not removed from the equation. If I set x plus 7 equal to 0, I get x equals negative 7. And since it did not cancel, since it was not removed, this is a non-removable discontinuity. In fact, this is a vertical asymptote. So when it cancels from a rational expression, it's going to give you a hole, a removable discontinuity. When it doesn't get removed from the equation, from the expression, it is a non-removable discontinuity. We can do the same things if we start factoring with problems that involve e to the x. This problem has e to the x minus 2 on the top. Now the bottom we can factor just like a quadratic. E to the x times e to the x is e to the 2x because you add their exponents. Now give me two factors of 8 that add up to negative 6. It would be minus 2 and it would be minus 4. Now what we're supposed to do is we're supposed to set each factor equal to 0. Well, wait a minute. Do you notice these cancel? When you do e to the x minus 2 equals 0, you're going to get e to the x equals 2. And then how do I solve that? I'm going to take the natural log of both sides. And I get x equals the natural log of 2. Now that factor was removed from the equation. So this creates a hole in my graph. It is a removable discontinuity. Okay? Now, the other one was not removed. The e to the x minus 4, if I set that one equal to 0, I get e to the x equals 4. And what I'm going to have to do there is I'm going to have to take the natural log of both sides again. And I'm going to get x equals the natural log of 4. Now, this was not removed. This is a vertical asymptote. It is a non-removable discontinuity because it was not removed from the equation. Now, we're going to do another problem with e to the x here. We're just going to jump down here to this f of x problem. Obviously, the top doesn't factor. Now, the bottom, if you recognize it, this factors into e to the x minus 3 and e to the x plus 3. Nothing cancels. So in this problem, I'm not going to have a whole. If I set this factor right here, e to the x minus 3 equal to 0, I'm going to get e to the x equals 3. And how do I solve that? I take the natural log of both sides. I get x equals the natural log of 3. Now, since this was not removed, this is a vertical asymptote. This is a non-removable discontinuity. Now, where we get kind of stumped here, e to the x plus 3, if I set that equal to 0, I'm going to get e to the x equals negative 3. That can't happen. If I happen to take the natural log of both sides, I can't take the natural log of a negative. This one gives me nothing. It doesn't give me a discontinuity. So this problem only had one discontinuity. Don't force the fact. Just because there are factors doesn't mean it's going to give you a discontinuity. Now, trig. Trig, you've got to remember two formulas. Okay? For tangent, for the asymptotes, it is x equals pi over 2 plus pi n. And what n is an element, I'm going to put a double bar z here, of the integers. N is an integer. You have an asymptote starting at pi over 2 and every pi units before or after that. Now, how am I supposed to find the asymptotes if it's 2x? This is really very simple. Take that 2x and just set it equal to the formula that you have for the asymptotes. Now, how would you solve that? You would divide everything by 2. So this would no longer be pi over 2. It would be pi over 4. This would no longer be pi n. It would be pi n over 2. This is where your asymptotes would be for tangent. Now, tangent, like I said, it doesn't have holes. It has vertical asymptotes. So these vertical asymptotes are non-removable discontinuities. Unless a trig function is modified with other functions, trig functions, your parent trig functions have vertical asymptotes for tangent, cotangent, secant, and cosecant. Well, what happens if I run into those other trig functions? Well, we're going to do secant first down here. And the reason we're going to do secant first is because it has exactly the same formula as tangent. It is, sorry, I picked the wrong one there. It is pi over 2 plus pi n. And again, n is an element of the integers. And really, you can use any variable you want. Okay? But what we're going to do, everything in here affects your vertical asymptotes, because vertical asymptotes are x equals. So what we're going to do is we're going to set that expression pi x minus pi over 4. We're going to set that equal to the vertical asymptotes formula, and we're just going to solve. Well, first thing I'm going to do is I'm going to add pi over 4. So that would give me 3 pi over 4 plus pi n. I'm just combining like terms, moving this over to here. Now, if I divide by pi, I get 3/4 plus n. Those are my vertical asymptotes for secant. It's really that simple. Now, for cosecant and cotangent, the formula is x equals pi n, where n is an element of the integers. So it has different formulas. The reason secant and tangent have the same asymptotes is because they're both something over cosine. And cosine has zeros at pi over 2 plus pi n. Well, cotangent and cosecant are both based on sine. Sine has zeros at the multiples of pi. So when you look at cosecant here, all you have to do is take that formula 1/3 x plus 2 pi And we're going to set that equal to pi n. So the first thing I'm going to do is I'm going to subtract the 2